So welcome to today's webinar. It's a great pleasure to introduce Fernando Quintana, who has worked extensively in Bayesian non-parametrics and has been chair of the section. And is perhaps, I guess, most well known for his work on product partition models, but all sorts of other parts of non-parametrics. And so today he's going to be talking with Matt Heiner and Garrit Page about some work on local regression. So I'll hand over to Fernando.
Well, thank you so much, Jim, for the invitation. Thanks to the section for this opportunity. And as you were saying, this is joint work with Matt and Garrit, who will be coming in later after I hand the screen to them. Okay, so this is, oops, sorry, that's it. So the quick summary of this presentation has to do with the random partition models that depend on covariates. And in particular, in the case where some of these covariant values could be missing. And we, of course, want to do something about that and hopefully be able to do predictions in a good way. So this actually grows out of previous work that we have done with Garrit and what is called the VD-Reg model. I will explain what all those acronyms mean later. And so on top of that, we want to add the ability of including covariates in the likelihood model. And remember that those can be missing values. Okay, so we're going to present the model, talk a little bit about the computation, simulation studies, and then applications to well-known data sets, and then we'll conclude in the end. All right, so the beginning of this, as I was saying, is the case where we have missing values in covariates. And of course, more generally, whenever people have missing values, kind of like almost a very quick reaction is to say, well, let's eliminate everything that has missing values and work with the complete case data. And you can do that, but of course, there is a high risk of having biases because of you don't really know what's going on. And so an alternative approach would be to say, well, let's try to deal with this incomplete data, in particular in the case of incomplete responses. And in that context, you have a very popular method, which consists of the multiple imputation. In the multiple imputations, you have some probabilistic way of filling in the holes, and then you can repeat that experiment several times and see how your method affects things related to inference, like parameter estimation, etc. And there are very famous references along those lines. And this is not meant to be a complete list at all. It's just a few references that are important from a historical viewpoint. All right. So the case, in contrast, of missing values in the covariates is much less popular in the literature. But still, and that's exactly what our focus will be, the case of missing values in the covariates, all right? So you can still play the game of doing this complete case data analysis, but it's been illustrated very nicely in this paper, Mercaldo and Bloom over here, that could be very poor performance, particularly when it refers to predictions, which is our main goal here. All right, so So what we do now, I said already that there was a previous work that builds on these product partition models with missing values in the covariates. And now what we want to do is to, on top of that, add the ability of including those in the likelihood. Why? Well, because, again, we want to improve predictive performance. That is our ultimate goal here, all right? And so by doing this, we'll have essentially something like that looks like mixture of local linear regressions with local weights by covariate values, all right? We won't be, our model won't be depending on particular what is missing or how the missingness patterns are given in the data. This is not a pattern submodel here, all right? And along the way, we found that sometimes adding covariates in the likelihood is not necessarily helping the ultimate goal of prediction, and we'll come back to that particular issue later. All right. So some references along this line. This paper over here deals with BART models, and it actually has the ability of incorporating missing covariate values. So what they do is in the splitting rules, they expand those rules to account for the missing covariate values, all right? So this one over here, the second one, doesn't deal with missing observations, but it shows the utility of incorporating local linear predictors and local linear regression in random forests. So in a sense, it's related in the spirit to what we're proposing. This paper over here does deal with missing covariate values, and it actually has imputation. So it's a combination of L1 regularization with spike and slab and some stochastic approximation EM to do variable selection in the context of missing values for the covariates. And this one, the last one over here, Chandra and others, it builds on essentially the same type of strategy to build the prior as we have done before. But with a completely different purpose of trying to, generate synthetic controls in clinical trials. All right, so let's start with the beginning. The beginning is these random partition models depending on covariates. So the row M here will be, this is a little bit of notation. It's going to be our basic object here, the partition into certain subsets. There is KM clusters. The xi will be the covariate vector for this particular individual I. Note that this has dimension p. Everything with a star will be collecting things by clusters. So x star j will be the collection of all covariate values for individuals in a certain cluster. I need more notation because we're going to be referring explicitly to what we observe. So the OI would be the collection of indices that are observed that have observed covariate values for a certain subject I. The superindex O will be, collecting things by the fact of being observed. The star with O is by cluster and observed. And then we have these things with two indices there. So the first index refers to subject or cluster in this particular case. And the second one refers to observation. So this would be all the subjects with observed covariate value for the else covariate, and same thing here, but now collecting the observed things for that particular cluster and that particular covariate. All right, so the PPMX, which is the beginning of this, is the modified version of product partition model. The product partition model, if you don't put covariates and use something like this, you will get the same, essentially something that is equivalent in terms of partition to the Dirichlet process, because you get the same, the ePPF. So the modification is to add this, what we call the similarity function. The similarity function has the role of being a function of the observed covariate values that is supposed to be larger when the x's are homogeneous. Okay, so the closer they are, the larger the value of the g's is supposed to be. And so what we want to do with something like this is to increase the clustering probability a priori, of course, by similarity of the covariate values. The way to define this, which we found particularly useful in many contexts and applications, is to express the similarity function as the marginal distribution under some completely artifact probability model, which the only role of this is just to give a formula for the G, all right? There are several advantages. I don't have time to go over those here, but let me just say that if you have several covariates, all what you do is to play the same game here and multiply these together. And one nice feature is that you can have mixed types of covariates very easily along this format. All right, so the VDReg, and we'll explain now what VDReg means, is essentially extending this construction to the case of missing covariate values. And in the case of missing covariate values, all you do is essentially, whenever there is something missing, which is indicated by this subset over here, you just skip it. Do nothing. Skip it over, and that's it. In an extreme case, if everything is entirely missing, you just have a 1 over there. All right, so nothing else. Okay, so that's the modification. And on top of that, what you do is to complete them. Sorry, the BDReg is because it is called the variable dimension regression. The variable dimension refers to the fact that out of all your covariate values, all the covariate vectors, when you have a missing entry, what you observe is of dimension less than p, and this can vary from covariate to covariate. Okay, so that's the variable dimension regression here. And on top of that, what you do is to build a standard model. In this particular case, what we did earlier is to put a sampling model, which is basically conditionally independence, no x over here. So all the dependence on x was built through the prior. There's no x here, and that is completed with some model for these cluster specific parameters. Okay, so I will now hand this to Matt.
Fernando, a quick question, if you don't mind. I may have missed it, but are covariates missing completely at random, missing at random, or not missing at random?
Yeah, that's a very good question. In principle, when we proposed this model, we tried both cases. We tried completely at random, we tried not completely at random, and we tried not random at all, like missing, whenever the x is large, we miss all of them, and that kind of thing. So we've played with this model under that context, on the context of exactly the model that's being shown there, and we still found good results. All right.
Okay.
So, but the construction is generic.
Thank you.
You're mute, Matt.
Thank you very much, Fernando. I was just saying that what I'm going to be talking about is built on an assumption of missing completely at random, but later the simulation studies do explore violations of that assumption. Okay, can you hear me and see this screen okay? Fantastic, great. So I'm going to spend about 5 minutes making a few observations that set the stage for our proposed model. One of the contributions of this paper is that we follow up and investigate on the behavior of the modification to the similarity function that Fernando has just proposed. And we do this with a pretty simple experiment involving 2 observations or 2 units, each with just 2 covariates. Because similarity functions are constructed to be based only on the distance between 2 covariates and not on their absolute locations, without lots of generality, we can fix the location of one of the observations at the origin, and then we are going to study the probability of co-clustering as a function of the 2 coordinates for the second unit. And we're going to do this with the standard default value for the precision parameter in the cohesion function, and then we'll study this for 2 similarity functions, normal normal and normal normal inverse gamma. So on the top row we have normal normal, the bottom row we have normal normal inverse gamma. I'm going to zoom in on the top row while we describe what's going on in these plots. So what we're seeing here is the probability of the 2 observations, the 2 units co-clustering as a function of, on the horizontal axis, the first coordinate of the second observation, and then on the vertical axis, the second coordinate of the second observation. And so if you go to the bottom left corner, for example, it's very close to the first observation's covariate vector. The probability of co-clustering is very high. So this is for the normal normal case. On the left, we have both observations, or both covariates are observed, and on the right, x2 is missing. And you get this for both, of course, for both of the similarity functions, though they have kind of a qualitatively different shape. But the point I'd like to make here is that these similarity functions are just probability densities. And the act of skipping over a missing covariate is the same thing as integrating over a missing covariate, just integrating it out of the similarity function. So that leads us to essentially our key observation that if you were to start with a vanilla product partition model where you were performing a joint modeling on y and x together, where for your model for x, you use the q's that were employed for the similarity function previously. If you do a separate q for each x independently, you have your joint model for y and x together. If you then go through and analytically integrate out the missing x's beforehand, your resulting inferences, your posterior distribution will be exactly equivalent to that of using the proposed VD-reg model with this new similarity function that was proposed in the last paper. This is very closely related to the computational trick that was noted in the original PPMX paper by Mueller, Quintana, and Rosner in 2011. So what does that buy us? I'd like to just take this point just a little further, talking about the marginalization property that you get from joint modeling. If you were to treat X random and do joint modeling of Y and X, which you get that advantage from doing the VD reg model. So once again, with a very simple example here to illustrate the point, consider y is just a nonlinear function here of a single covariate x observed with Gaussian noise. And you could fit your favorite nonlinear regression to this if x is observed and get that conditional Gaussian distribution for y, no problem, right? However, what the question now is, what would you do if x were missing, in particular, if x is missing at random and you don't want to perform imputation? If you did impute the missing x, you would still be able to recover this marginal distribution for y that we see here on the right with this histogram. But what would you do if you're not going to impute the missing x? You could fit maybe a separate model for when x is missing. The advantage of using marginalization, though, is that it helps you if modeling the response distribution is important to you. Of course, you know, a conditionally Gaussian model is just not going to pick up this marginal distribution. And this concept applies to higher dimensions of covariates of higher dimension. When you're talking about different missingness patterns, you'd then be talking about partial conditional distributions. So with those concepts in mind, we know that the proposed VD-reg model possesses that projectional or marginalization property without resorting to imputation. The question now is, can this be done using linear predictors in your sampling model or your likelihood? So to consider that, we're going to step away on this slide. We're stepping away from the PPM or PPMX model and consider the marginalization properties of the multivariate normal distribution. And we'll take a very specific setup here. Consider a joint model for y and the vector x, where each x gets a univariate normal distribution right here. And then we'll specify y conditionally on the vector x as this normal with a linear predictor, where the regressors here are centered and scaled by the parameters that were in that original normal distribution, those original normal distributions for x. If you take that as your joint model, and you then take that joint density and integrate with respect to certain x's, these will be the x's that are missing, you get this representation on the bottom of the joint density. This joint density factors in this way below here. So you see immediately something that's very similar to what Fernando proposed with the VD-reg model, that the similarity function just skipped over the missing x's. You see right here, these auxiliary models for x are involving a product only of the observed x's. And then your conditional model, this piece will end up serving as our likelihood. What we have here is an automatically adapting linear regression, where the linear predictor involves only the covariates that were observed, and then we inflate the variance according to the missingness pattern, and with the squares of the coefficients of the missing x's. So this setup right here automatically adapts to any missingness pattern without requiring new kernels or any additional parameters. So this model here on the bottom is what will serve as the basis for our proposed sampling model. Before I get into that, though, I want to emphasize that unlike the previously proposed VD-reg model, the one that we're going to propose now does not have an equivalent joint model that it descends from. Instead, this model that we're developing is a purely conditional model, sampling model, that just mimics the marginalization behavior and does so without imputation. Another kind of subtle issue here that comes into play when you introduce this likelihood or sampling model is that these the centering and scaling parameters, these parameters are shared. They belong to the similarity as well as to your likelihood, which if you put that into a PPMX model, that comes with a lot of baggage. So we're going to dissociate these parameters from the similarity functions and from the likelihood. So these centering and scaling parameters here will not actually be model parameters for which we perform inferences, but instead we're going to use plug-in estimators right here. For example, you could use maybe the empirical mean for the set of x's that belong to a certain cluster. Rather than just going straight for the mean, though, we're trying to encourage smoother behavior, and we'll use Bayes plug-in estimators at that point. Okay, so here is the full hierarchical representation of our new model that we're proposing, the VDL-reg. That's variable dimension local regression model with a dynamically centered likelihood. The second through fourth rows right here are equivalent to that of the original VD-reg model, with the exception that we now are introducing these regression coefficients for each cluster. And now we see this dynamic likelihood that involves the covariates, only the covariates that are observed for that observation, that unit, and then with this adaptation dealing with missingness. And you can see we call this dynamically centered because, once again, the regressors are these z's that are centered and scaled versions of the covariates. They're centered and scaled using a Bayes plug-in estimator under a condition or under a conjugate prior that you see there along the bottom. One thing I'll mention here is that if you fix all of the betas equal to 0, you'll notice just these terms disappear and you immediately recover the original VD-reg model. But another issue that we run into with this inflation of the variance, if you're not careful to regularize the betas, you can just get too much inflation of the uncertainty and left with a not very useful model. And so we aggressively shrink those coefficients towards 0. You could use your favorite shrinkage prior for regression here. We chose to use the Dirichlet-Laplace prior in this case. Speaking about prediction under this model is fairly standard. If you want to make a prediction for the next observation, you first need to consider its allocation to one of the clusters or to a new cluster. And here you have the same EARN scheme that you're used to. I want to point out here, though, that the predictive distribution under this model has a mixture form right here, that the weights, they come from these probabilities of belonging to the different clusters. And of course, so this this mixture form with the adapting variances gives you the internally consistent uncertainty propagation for any that accommodates any missingness pattern without introducing new parameters. That's really nice. You can accommodate multimodality in those marginal or partial conditional distributions. And I also want to point out that because the weights in this mixture, the weights as well as the conditional means in the kernels, both depend on the covariates. And so that gives you, with the corresponding mean surface, that gives you general nonlinearity of that surface. So these points are what I just talked about. You have the weights and the means depending on covariates. Predictions are possible for any missingness pattern that appear in the data, including you can make predictions for any missingness pattern, even ones that did not appear in the original data set. And these last two bullet points are kind of technical issues that we won't get into right now. I'd be happy to talk about them later, but the first one is just saying that there doesn't exist an explicit mapping from Y to X under this model. It passes through, and it only exists, your mapping from X to Y in this model only exists within the context of your X matrix from the training data. All right, so I'll talk for a couple of minutes about some practical aspects of this model. First, MCMC, and our strategy for MCMC is fairly standard for these types of models. One thing to make note really quickly is that with our involving the coefficients to inflate the variances complicates the updates for the regression parameters, and we deal with that using an elliptical slice sampler. The other issue that comes into play here is with the full conditional distribution for these the discrete latent allocation variables for each observation. So this full conditional distribution should look familiar. It's this EARN scheme again, but in the traditional update, your likelihood contribution to these full conditional probabilities involves only the ith observation, whereas now we've complicated the likelihood with this dynamic centering. This update now involves the entire data set for each one of these allocation updates, which of course makes this much more computationally expensive. So we're not going to use this full conditional distribution. We're not going to use the famous algorithm 8 from Radford Neal. Instead, we're going to use algorithm 7. Props if you can remember what algorithm 7 involves. What it does is it allows us to, instead of evaluating the likelihood for every potential cluster, it allows us to do it for only 2 clusters at a time, because it's a Metropolis Hastings proposal. It proposes one of 2 types of moves, either moving from a singleton to a group or a group to a singleton, or a move between 2 occupied clusters. And this helps us because we can evaluate the likelihood contributions of only 2 clusters at a time. And we modified this algorithm in the sense that our proposal distribution does not involve the likelihood evaluations. The proposal distribution only comes from the similarity functions, and we can get away with that because in these types of models, the posterior over the partitions is generally dominated by the similarity functions. One other quick practical issue that we can talk about involves these 2 questions. First, is it worth all the extra computation to add the linear predictors into the likelihood? And second, would adding those covariates to the likelihood always be beneficial for prediction? Of course, you can imagine a simple scenario where it wouldn't necessarily, if you have several different clusters and the response with those clusters is just a constant plus noise at each cluster. And even in that case, if you tried fitting the local linear model, sometimes you could have, or that we've seen in practice, you might have two well-separated clusters and the model attempts to fit a line connecting those two separated clusters, which would deteriorate the quality of the fit. So in response to this, we've developed a fast screening tool that you can run quickly without having to commit yourself to fitting the VDL-reg model. This uses model-based clustering as implemented in the mclust package. What we do is we whittle it down to modeling just the complete cases in the data, and we concatenate Y with X. So we treat it like we're doing joint modeling of everything. We throw that into mclust, get an estimate of all the different clusters, and then within each cluster, fit a regression model of Y on the X's. And within each cluster, then you can get the statistics out of that. You look at the coefficient of determination, the p-value for the global f-test. And if you want to combine all of these into a single indicator variable, maybe you could do something like a weighted average of those statistics to help you decide if it's going to be worth fitting a model with local linearity. Of course, the local linearity indicator here based on the results from mclust would not be the same as what you would get from VDL-reg. First of all, because you're considering only the complete cases, but also because mclust considers various different covariant structures. So I'll turn time over to Garrit now to talk about simulations.
Great. We leave this just on, right?
Mm-hmm.
Okay. All right, I'm just going to spend a few minutes talking about some of the results we had from some simulations and a little example that illustrates a little bit about the benefits of thinking or considering VDL-reg has. And so I get the good job of showing the good stuff associated with this particular model. So to start out, we're just going to consider a little bit of a toy example with simulated data. And these simulated data have 500 data points with 2 covariates. And within these data, we generated 3 clusters. And within each of the clusters, we had a different a regression model that is described here in bullet point 3, where we have the cluster-specific slope and intercept values. And we fit the model that Matt just described with the computation that he just described, and based on that fit, then we estimated the partition using David Dahl's Salso algorithm to get an idea of what the partitioning is. And the result of that will show you one particular synthetic data set we can see here. So this plot on the left, we have the complete cases where Y is on the vertical axis, you have X1 and X2. And this 3D image was rotated in a way that kind of corresponded to what we would see when we consider just the X2 as missing. And so on the right, we have the results when we kind of essentially marginalize over X2, or X2 is considered to be missing. And we want to highlight the fact that without having to specify, just with specifying just the VDL-reg model, we were able to do quite well in capturing the clustering in a very nonlinear way. We just missed a few points in red and a few points in blue, obviously. As you see from the dark filled-in points are the ones that we did correctly, and the non-filled-in points are the ones we did incorrectly. But overall, quite satisfied with this idea of being able to capture this clustering without having to specify any type of different kernels for the different X's, and just essentially, as Matt explained, marginalizing over the missing. And in addition to that, talking about tagging on to what Matt spoke a little bit about, the idea that when you do consider a missing X and you are only marginalizing over that to consider the response distribution for one of the given X's, it could result in a response distribution that becomes bimodal or that has multiple modes. And we see that in this particular dimension of the synthetic data set. Once again, on the left, we have the full data and rotated in a way that it's easily to compare what happens or to see what's happening when we go over to the case when X1 is missing. And in this case, we now have a response distribution that is multimodal and has obviously regressions going in different directions. And even with that in case, we did quite well in recovering the clustering without having to specify any type of different kernels for the different dimensions, apart from where it's really challenging to cluster those individuals as there's a bit of overlap on the clusters there. And even more cool in a way is when we have X1 and X2 completely missing. And so this borrowing the strength, I guess, if you will, over the different dimensions allows us still to recover some of the clustering. On the right there is just the Y when X1 and X2 are both missing. And notice that we're able to capture some of the clustering that goes through these red points, right? There's some clustering below and above it, which is quite a cool feature when we're not considering X1 and X2 in the model at all, and we're kind of marginalized over to Y. And this VDL reg allows us to pick up this particular structure in the data by formalizing a model for the X and the 2 there. So we thought that was pretty nice to see those types of results, particularly being able to recover the clustering by just simply skipping over the X that is missing. We did another simulation study that was more formal in generating a number of data sets to see how we perform in prediction. In this simulation study is based on the Friedman data, which is quite famous now, where we fixed 10 covariates, and those 10 covariates are all generated using uniform 0, 1. And then the response values for each of the generated covariate values is produced by this particular function that we see right here. Notice that X6 through X10 are simply noise. They're not impacting the response in any way. We just have X1 through X5 that are impacting the response in a very nonlinear way as well, right? Another thing to notice here is this data is not generated in a way that the clusters are explicitly introduced in the data generating process. And so we're seeing how our method can do when X is not informing clusters directly. We wanted to see what happens. One factor we consider is the different types of errors. We had IID noise, and then we had some noise that depended on X1 to see how we performed in that scenario. And we generated data where we had X's that were missing at random and not at random. We'll only be talking about the at random because the patterns that we saw in not at random are very similar. And those are contained in our paper that's going to be available soon. And we generated 300 training samples, and we also generated 300 testing observations for which we can compare the predictive performance of our method relative to a few others. Now, how did we evaluate the performance of being able to estimate the response distribution and also do some prediction? We use the typically used mean squared prediction error, the mean squared error for in sample or out of sample. The problem here is mean square prediction error is perhaps not a completely appropriate metric to use in evaluating these methods, particularly when the response distribution is multimodal. Due to that, we've also incorporated 2 other metrics that permit us to evaluate how well we're recovering the entire response distribution based on whether X1 or X2 or any of the X's are missing. One of these we call goodness of fit. And it is simply looking at the quantiles associated with the response distribution, and then looking at essentially the Kolmogorov-Smirnov test statistic for the uniformity of these QIs. Once again, here, smaller is better. So smaller is better, and obviously in the MSPE, smaller is better also in this goodness of fit metric. And then we also considered this deviance, what we call the mean deviance prediction metric. And we're essentially evaluating the likelihood, this Monte Carlo estimates of the log likelihood, and then just looking at this particular value there for VDL reg, We can also see that we can recover that quite easily for VD reg by just setting those coefficients equal to 0, and then the deviance is just -2 times the average, the typical average of this likelihood. And once again, smaller is better in this particular case. So with that in mind, these are the results of the simulation. Oh, sorry, I forgot to introduce the values for the methods to whom we're going to compare. So we're going to compare BART with as implemented as BART machine package, and that permits missing. And we also considered a random forest that implemented miss forest, and then we consider pattern submodel, and then multiple imputation is to give context to our comparisons. And so this is the results for missing at random. We'll focus in on, so the top row is the mean square prediction error, the middle row is the mean prediction deviance, and then the last row is goodness of fit. And then the two columns are constant variance and unconstant variance. With regards to mean square prediction error, thanks for zooming in there. With regards to mean square prediction error, BART was very competitive. And as the percent of missing increased, I'm sorry, I forgot to say this, on the x-axis, what we're doing is we're increasing the percent of missing from 0 all the way up to 50%. And as the increase in missingness, as the percent of missingness increased, the methods tended to do similarly. Now, if we focus in on the mean square deviance, VDL reg does quite well relative to the competitors. VD reg and BART are very similar, and the difference between the competitors, similar to mean square prediction error, decreases as the percentage of missingness increases. And multiple imputation does the worst in that particular metric. And then as we look at the Kolmogorov-Smirnov metric, BART performs the poorest in this regard, and the other three methods, multiple imputation and VD reg and VDL reg, perform very similarly. So overall, with this, the take-home message for this particular simulation study is VDL reg does a good job in recovering the entire response distribution relative to some of its competitors. And with that, turn the time back over to Matt.
Okay, and I'll finish my part talking about a couple applications. We just have two demonstrations on very familiar data sets that highlight different aspects of this modeling here. So the first is the Boston housing data. The missing BART paper used the Boston housing data. We'll follow their lead in using 8 continuous covariates, where the response is the median value of owner-occupied homes for each of 100 or 506 census tracts in Boston. Before showing the results from the fits, we ran the linearity indicator test that I introduced earlier, where M+ gave us 5 clusters, and we have a weighted average of very small p-values, which may not be all that meaningful with a large data set, but we have pretty large R-squared values as well. So this suggests that it might be a good idea to include locally linear models here. The data originally do not contain any missing values, so we're going to impose missingness in the covariates completely at random, and we'll compare with all of these different competitors at different missingness rates. And what the box plots we'll see next are averaged over, or we're seeing these over 100 replicate data sets, each of size 400, and then the methods are evaluated on the remaining 106 observations. All right, so for mean squared prediction error, you may not be surprised to see that random forest and BART really shine here in point prediction, and still perform well as you increase missingness. But another take-home message here is that the VDL reg, the proposed VDL reg in blue, consistently does better than the VD reg model, which is not including the local linearity. And that seems to be consistent with what we saw with the local linearity indicator. And then if we move over to the predictive deviance, we see that the PPMX-based models are perhaps handling the marginalization better to capture the response distribution with different missingness patterns better. It's also instructive to see how many clusters each of the models are fitting. The VD-Reg model consistently fits, on average, about 3 more clusters than the VD-L-Reg. The other example is using the Old Faithful geyser data. This is from the Old Faithful in Yellowstone National Park. It's a time series from 1985. It's a 2-week window in 1985 of successive waiting times between successive eruptions of the geyser. That's our response variable, and we're going to use up to 3 covariates: the duration of the previous eruption of the geyser in minutes, then the first lag of the response, the waiting time to the previous eruption, and also the second lag of the waiting time. For purposes of illustration, we're going to impose missingness based on eliminating observations that were rounded to whole numbers. In 1985, they didn't have somebody out there measuring the duration at night, I suppose, and so they had qualitative nocturnal measurements for the duration, but we're just going to eliminate those and treat those as missing values. So once again, we do these 100 replicate training test sets, and we're going to repeat this under the 3 different combinations of covariates, one involving only the waiting times and the lags of waiting times, one involving the first waiting time and the duration, and then one involving all 3. Because the evaluation metrics are so similar between all the methods in this example, these plots are reported as pairwise ratios against VDL-Reg, so using VDL-Reg as the baseline. So VDL-Reg, the blue one, it does perform the best in mean squared error, but they're all very competitive here. And then it's decidedly best in the predictive deviance. But the plot that's really interesting about this is that the Old Faithful data are really nice for demonstrating these marginalization properties of this model once again. There's a lot to unpack here, so I'll try to describe what's going on in this plot. First of all, we're looking at a scatter plot of the waiting time variable on the x-axis versus the response variable on the y-axis. And each row is giving us a different slice of the 3D scatter plot. So we're for different values of the duration variable. So on the top row, duration is 2. On the second row, duration is 4.4. And on the bottom row, duration is missing entirely. The size and the opacity of the points is showing you how relevant these points are in this slice. So on the top row, the really large points are duration values that are close to 2, and the ones in the background there are less relevant. Those are durations further away from 2. The red curves are just the mean, the estimation of the mean functional there, and the dashed one is the estimate from the missing BART. And the coloring on these is evaluating the predictive density from our models on a grid. On the left, you have the original VD-Reg, and on the right, you have VD-L-Reg. So let's start with just a quick comparison of VD-Reg and VD-L-Reg. You don't buy a whole lot of savings in terms of clusters in this case, but you can kind of see on the left here, it is using 2 clusters. It's splitting up into 2 clusters to try and fit that linear trend on the bottom right, whereas the linear model, it's, of course, the local linear model is just fitting that linearly there. The other thing that's really interesting to see here is when duration is missing. On these plots, all of the points do appear, even if D1 is present. The missing duration values are the circles here. But the point here is that the model fit uses all of the observations. This is not like a pattern submodel approach where you would fit this, when duration is missing, you would only fit the missing duration observations. This is using all of the data. And it's also demonstrating the internally consistent marginalization property of the model that adapts to any missingness, automatically adapts to any missingness pattern with no new clusters, no new parameters. It's just simply adjusting to the information at hand to correctly capture the bimodal conditional distribution of Y in that case. Okay, and so with that, we will turn it back over to Fernando. Fernando, you're muted.
How about now? Perfect. Okay. All right. So just to wrap it up, quickly, there is no paper right now. I mean, the final version of it, we're working through it. So if you're interested in this, you're very welcome to check the archive. There will be a paper hopefully next week or in the next 2 weeks or so. So basically, we think this is an interesting story. So the VDL-Reg model builds on the previous VD-Reg model, but basically it gets the ability to incorporate likelihood, covariates in the likelihood, with the hope that that will improve predictions, and that's the whole point here. And of course, we repeated this several times, we completely avoided any kind of imputation, even though there was some marginalization or projection, if you want, that basically aimed at precisely trying to do what we were saying. The computation here, as Matt was describing, is a little bit more involved because of this centering that happens at using all the covariate values from the clusters. Okay, so that requires a little bit more computation, but it's not terribly super much more heavy than the typically loaded versions of the models that you have to deal with in this context. The other thing that we believe it's interesting is this notion of going beyond mean square errors. Oftentimes what you find is distributions that are multimodal or asymmetric or heavy tails, etc., etc. In that particular context, the question is there anything else that we can try? And of course, there are many alternatives that we could use here, but essentially we found that this predictive deviance or the Kolmogorov-Smirnov test for quantiles were useful options, and there are more, of course, but these are some alternatives. Essentially, the idea is to look beyond the mean square error or the mean square predictive error. Another thing that came up along the way is this local linearity thing that I believe we need to explore a bit more, but it could be useful as a tool, you know, to get a quick, because computing that is very easy. It's just a few lines of R calling this unclust package and computing the weighted average of the regression summaries. It's very easy to implement. And in a matter of seconds, you can have like an indication where there is some worth of trying to add this covariates into the likelihood. And I guess that would be all for our part. There are some references over here, the things that came up during the talk, and many thanks. Muchas gracias.
Thank you. Thank you. It's a very interesting talk. So are there any questions for Fernando, Matt, and Garrit?
I have a small one, and I may be off base entirely. I was intrigued by the predictive deviance approach. That's interesting. My understanding is that deviance requires nested models, and I did not see the nesting. Did I miss it?
I can take that. So this is, we're calling it deviance simply because it is the predictive density value multiplied by -2, just so that it's on a scale.
Yes.
That it's comparable, but this really is just predictive density evaluation.
Okay, thank you.
Alessandra?
Hi, thank you very much. Really an interesting paper, and I wait for it. Just a question. I mean, I see that it's not the main focus here. The focus here is on the percentage of missing data that you have, but it's your, let's say, model or algorithm somehow robust with respect to the dimension of covariates or the dimension of data points. Because, I mean, you have shown the dimension in your examples, the largest dimension of your covariates was 10, if I remember correctly, right? And
yes,
the response was 1 or 2.
We used in the simulation study up to 10 covariates, of which 5 were noise. So we didn't explore super much how many covariates we could reasonably fit into this particular framework. But we did explore partially what you were asking, so we could have up to 50% of missingness over here, and we tried that on several replications of our simulation studies. So I guess it all depends on when the computation breaks, the number of covariates that we can try. In the previous approach, without the covariates in the likelihood, we went all the way up to 25 or something on that range, or maybe 30. Mm-hmm. It wasn't the idea to try to explore how many covariates we could add. The other thing that is important to remember here is that our prior for the regression coefficients has this, it's this Dirichlet Laplace, which is basically aimed at trying to control, to try to shrink aggressively all these coefficients to 0. And so the hope would be in that particular case that if there are many noise things, those will be taken care of by this Dirichlet Laplace prior over here. So that is kind of like a partial answer.
Yeah, thanks.
Are there any other questions? Okay, so I had a question, I suppose. So it's interesting that you do a lot better than BART in terms of kind of calibration, right? In terms of the probability integral transform, things like that. So do you have any thoughts about why BART is doing better in terms of mean squared error in some of these examples, and how you would need to adjust your model to compete better with BART, or whether that's possible on that kind of measure?
My belief about BART is that it is it's especially good at point prediction because it so efficiently cuts through to at discriminating and figuring out the relevant covariates and figures out the partition very efficiently. It essentially does its own variable selection, and so BART is very good at getting those point predictions and does so very efficiently, whereas these models with the similarity functions, especially when you get into many covariates, we're not incorporating variable selection in here. And when you get into very high dimensions, you can imagine these densities in high dimensions. You have kind of the cursive dimensionality defining what becomes a cluster. And so it's just perhaps less efficient in that sense. Also, the BART models, we noticed consistently that the results from the BART models are getting an under-dispersed predictive distribution. So I think the BART models, I suspect, I haven't verified this, but I suspect the BART models are setting a strong prior on their variance to encourage flexibility in the regression, targeting specifically point estimation, point prediction.
Yeah. Okay, that's thank you. That's a good explanation. Yeah, so it kind of fits with the folklore, right? That BARD is good for mean prediction.
Right.
Yeah. So, are there any other questions?
Something in the chat.
Something in the chat.
Something in the chat.
Is that a question?
Oh,
Someone's off.
No.
Okay.
Sonny had to go.
Yeah. Okay. Well, thanks for the talk. It's very interesting. And we'll see you all next month for the talk in March. Bye.
Bye.
Right, see ya.
Thank you.
Thanks.
Bye, guys.
Thanks.
Bye all.